Everything around us is in motion. A car turning a corner, a planet circling the sun, it can all look pretty chaotic. But what if I told you it all follows just a handful of simple, elegant rules that are hiding in plain sight? Well, let's pull back that curtain and take a look at the invisible rules that choreograph, well, pretty much everything.
We've all been there, right? You're just standing on the bus, minding your own business, when the driver slams on the brakes and suddenly you lurch forward. That feeling? It's not random. It's actually our first major clue, a breadcrumb that leads to a deep, universal truth about how the cosmos works.
And yeah, that feeling on the bus, that brings us directly to our very first rule. You could almost call it the universe's law of laziness. It's this fundamental idea that things just, well, they just don't want to change whatever it is they're already doing. And it affects everything, from a tiny speck of dust to the biggest star in the galaxy. Now, this cosmic laziness has a proper name, inertia, and it's really simple when you break it down. Objects are just plain stubborn. They want to keep doing what they're doing. If something is sitting still, it's perfectly happy to just keep sitting still. If it's moving, it wants to keep moving in a perfectly straight line at the same speed forever. It fights against any change to its situation. The legendary Sir Isaac Newton put a name to this idea. He called it his first law of motion. And here is the absolute key to the whole thing. An object's motion never changes by itself. It just can't. For any change to happen, something from the outside, what physicists call an external, unbalanced force, has to show up and mess with it. So, let's go back to that bus. The bus itself is forced to a stop by its brakes. But your body, thanks to inertia, it wants to keep cruising forward. And that's the jolt you feel. This is exactly why we have seatbelts. They provide that outside force to stop you along with the car. It's the same exact principle when you shake a rug. You yank the rug, but the dust, because of its inertia, just stays put for a second. And that's how it separates. Okay, so things only change their motion when a force gets involved. But what even is a force? How does that work? Well, that leads us right into our second major rule. This sort of universal push and pull that secretly controls every single interaction in the cosmos.
Now, interestingly, we're going to jump ahead to Newton's third law here, because it explains this idea of force so well. And it is a big one. It tells us that forces never show up alone. They always come in pairs. Anytime you push on something, that something pushes back on you with the exact same amount of oomph. No exceptions. And here's the part that really clicks it into place. These two forces act on different things. When you walk, your foot pushes the ground backward. That's the action. What's the reaction? The ground pushes your foot, and by extension, all of you, forward. Just think about that. You can't even take a single step without pushing the entire planet. And what's so amazing is how this one simple rule scales up. A swimmer pushes water back to glide forward. You push the earth down to jump up. A rocket shoves hot gas down with incredible force so it can blast off into space. It's all the same thing. The very same physical law that lets you walk across the room is what carried humanity to the moon. Incredible. All right, so we get it. Objects are lazy, that's inertia. And forces come in pairs. But how do we connect those two ideas? How much does an object's motion actually change when we apply a force? This is where Newton's second law comes into play. And it gives us the answer with one of the most famous and powerful equations in all of science. F equals m times a. Force equals mass times acceleration. Just picture yourself at the grocery store. Pushing an empty shopping cart? Easy. A little nudge and it's off. But a cart that's full to the brim, you gotta really lean into it to get it going. So why is that? Well, the full cart has more mass. And according to our new friend, F equals m, if you crank up the mass, you have to crank up the force to get the same acceleration. And the absolute beauty of this little formula is that it lets us predict things. We can actually run the numbers. Let's say you've got a 2-kilogram object, and you want to make it accelerate at a rate of 4 meters per second squared. You just multiply the mass times the acceleration, bam! The answer is 8 newtons. You know precisely how much force to apply. It's that simple equation that runs pretty much all of classical physics. So now we've got the fundamental rules down. But physics isn't just about the why of motion. It's also about predicting the how much and how far. And this is where we get to go from just observing the world to actually predicting it. It's time to open up the physicist's toolkit. Okay, so this toolkit comes with one big condition. It only works when an object's acceleration is steady and constant. So think of a car speeding up smoothly on the highway, or an apple falling from a tree. Gravity provides a nice, constant acceleration. In situations like these, we have a set of 3 special equations that let us see into the future to calculate exactly where something will be and how fast it'll be going at any point in time.
And just like any good toolkit, the key is knowing which tool to use for which job. It really just depends on what info you have and what you're trying to figure out. If you know the time and you need to find the final speed, you grab that first equation. If you know the time and you need to find the distance, you use the second one. And what if you don't know the time at all? No problem. The third equation is designed for exactly that situation. Let's actually try one out. Let's say a car is starting from a dead stop, so its initial velocity, u, is 0. It then accelerates at a constant 2 meters per second squared, and it does that for 5 seconds straight. How far did it go? Well, since we want to find distance, and we know the time, we'll grab our second equation. We just plug in the numbers, and out pops the answer. The car traveled exactly 25 meters. See? We just used a bit of math to predict a real physical event. So let's just take a step back and bring this all home. We started with a simple, everyday question about being on a bus, and it's led us to this incredible hidden architecture that governs all motion in the universe. We've uncovered 3 massive rules in a seriously powerful toolkit. First, we have the law of laziness, also known as inertia, which is all about how things resist change. Then we found the universal push and pull, the idea that every single force has an equal and opposite reaction. Then we got the master key, F equals ma, which perfectly links force, mass, and acceleration. And finally, we opened the predictive toolkit, which lets us calculate the future of motion.
The thing is, these rules aren't just for physics classrooms. They're happening all around you, all the time. Every step you take, every time you throw a ball, it's all right there. So the real question I have for you is this. Now that you can see these invisible rules, what other hidden physics are you going to notice in the world around you today?